Hey everyone, welcome back. Today is going to be the last challenge in the microcorruption series. Today's challenge is going to be Chernobyl. If you haven't watched this series of microcorruption, or if you are a new subscriber that is coming to watch this video, then you should absolutely watch this series of videos because this series of videos is basically practicing reverse engineering and binary exploitations at the same time, where I have explained the majority of, let's say, the pretty famous vulnerabilities around binaries, yeah, and we basically practice them on the MSP 430. Yes, so I think this challenge took me 6 days, almost a week, just to solve it. But since I was having work and all that kind of stuff, I was just investing 2 hours per day just to solve it. So yeah, so in this video we'll be learning about hash tables, about how hashing and rehashing works in hash tables, and we are going to basically reverse engineer a lot of things in this challenge. So this challenge is the hardest challenge by so far. So if you have solved the challenge, then congratulations. This challenge is a really awesome one and I really loved it. Yes, so don't forget to follow me on Twitter and don't forget to hit the sub button if you are completely new to this channel. And let's not waste too much time and see what we have. So, overview. So this log contains the all new log ID Pro account manager. So it has a lot of things. So there are no accounts set up on the Log ID Pro account manager by default. So an administrator must first initialize the log with user account and their pins. So user accounts are by default not authorized for access, but can be authorized by attaching the account manager authorizer. So to be authorized, you have to attach something called the account manager authorizer, which is a kind of hardware that you should be having access to in order to authorize the user. So this prevents users from adding themselves to the lock during its use. Okay, so this is interesting. So if we try to run the program, what do we have? So you can open the door by entering access, your name, and PIN. So for example, if we send access, I want to access, for example, with item byte and 123, for example, as a PIN. No such a box. Okay. For now, we don't have any kind of idea of what is this program is doing. The good thing about this challenge is that the code is not obfuscated as the previous one as Hollywood, so I didn't have any hard time understanding the code, but um, I really had trouble just reverse engineering and understanding what is happening exactly inside of that. So if we copy that, we should be having this code. Okay, so the interesting thing that I did is that I tried to statically reverse engineer every assembly instruction that was in here, especially for the main function. So if you go and search for example, for the main function, we should be having this one, which is going to be allocating some space on the stack, and then it is going to be calling the run function. Okay, it is going to be calling the run function. So if we try to check the run function, what is going to be having? So the run function is going to be having those things. So the first thing that is going to be doing, it's going to be saving the states of the old registers. So something that we have seen in a lot of challenges. Then it's going to be allocating 0x600 bytes on the stack, which is by adding this negative value to the stack pointer. Then it's going to be passing down two arguments, the argument 1 and the argument 2, which are 5 and 3, to the create hash table. Okay, for now we will be skipping what the create hash table is going to be doing, and then the result is, which is going to be in the register 15, is going to be moved on to the register 8, which is the address of the first entry. For now, let's just skip what exactly an entry is, because we'll be reverse engineering the create hash table, and just by dynamically looking at the memory, we will understand what an entry is and all of that. So we then have the welcome messages, which are those which are the usual welcome messages that we had. And then we start initializing the stack with 0. So how do we do this? So we clear the register 14, I'm sorry. We initialize it with a 0, and then we move 0x7 5ff into register 7, which is actually 0x600 minus 1, and then we jump to this address, which is this one. So we compare the resistor 14 with the resistor 7. So if the resistor 7 is greater or equal than resistor 14, then we jump back to this instruction, which is going to be moving the stack pointer to the resistor 15, and then adding what's in the resistor 14 as a counter to the resistor 15, which is actually the same as saying the stack pointer plus I just if you just knew the counters as, for example, I. And then you are going to be moving 0 to the register 15 to the address pointed to by register 15, which is why and then we increment the register 14. So this is basically is just going to be zeroing, let's say, the stack. So it's just cleaning up the stack with zeros. Next thing, we have we are going to be moving 550 to the register 14. So this is basically the size, and then we are going to be moving the stack pointer to the register 15, and then we are going to be calling the get string. So we are basically reading data to the top of the stack, since the destination is the stack pointer, and we are basically reading this size. Next, what do we have? So we are going to be moving the stack pointer to the top of the stack into register 11, and then we will be jumping to this address, which is this one. So we will be getting what's in the register, what's pointed by the register 11 into the register 15. So we are basically getting the first character of the input that we gave, and then we test if it is 0. So if it is different is 0, then we will be jumping back. So we will be checking if the first character of the input is A. How do we do this? By comparing the register 15 with the byte 61, which is a lowercase a. So if it is an A, then we jump. So if it is different to the A, different to an A, then we jump into another check that is going to be checking if the first character is a lowercase n. So if it is different to a lowercase of n, then we are going to be jumping to an invalid command message, and we can check that by checking the address pointed to by 4b55 54, I'm sorry. So if you go to 4b54 4b ABC 4B 54. Yeah, so this is basically the invalid command. Yeah, so this is the message pointed to by this address. So 4B 54 is pointing to invalid command message. So that means that it is an invalid command message. So to be invalid, so to make the command valid, it should be starting by an A or an N. So this is basically what is happening. So if we go back a little, now if we go to the first A, so let's assume that the command is starting with an A. So if it is starting with an A, then we move the register 11 into the register 14, taking in consideration that the register 11 is pointing to the top of the stack or to the beginning of the input. Now I'm going to be assuming that the input is like that. It's going to be access, a name, and a pin. So now register 14 is pointing to the A, which is the first character in the input that we gave. And then we are going to be adding 7 to the register 14, which means that now the register 14 is going to be pointing to the name, because we are actually saying that register 14 is going to be adding 7, and register 14 is already holding the stack pointer, so it's stack pointer plus 7, which is the name offset inside the input, which is basically the offset of the name inside of the input. Next, what we are going to be doing is moving that offset of the name into register 11, and then we are going to be jumping to this address. So this address is going to be taking the character pointed to by register 11, which is the first character of the name in this case, and then it's going to be testing if it is 0. So if it is different to 0, then we go back a little and we check if the character that is in the name is equal to a space or not. If it is a space, so the first step is if it's not a space, then we increment the register 11, and then we keep testing, and if it is a space, it's going to be checking these two instructions. So so if we hit the end of the name, he will be setting the ending of that name as the byte 00. So he will be basically changing that space with a null byte to say that this is the end of the name. So he is basically just parsing the name out of the input and then changing the space with a null byte. So it's pretty common way to do this just using this loop. Next, after doing that, we jump to the next instruction, we actually jump to the next to the next uh, to the next instruction, which is 4b e2. So we increment the register 11, and now it is pointing to the offset of the pin. So basically, by incrementing the register 11, we take in consideration again that the register 11 was pointing to the latest character on the name, which is actually this space. So by incrementing that register, it's going to be pointing to the offset of the pin now. We initialize the resistor 10 to 0, and then we jump to this address, which is going to be doing the same pattern as the other one, which is going to be taking the character pointed to by resistor 11 into resistor 15, and then he will be testing. If it is a 0, then he will be jumping to this block of code. Otherwise, he will be comparing the resistor 15 with the 0x3b, which is basically semicolon. So if it is semicolon, then he will be jumping to this one, which is he was actually trying to calculate something inside of the resistor 10. So he will be moving, so taking in consideration again that the resistor 10 is initialized with a 0, he will be moving the value of the resistor 10 inside of the resistor 13, and then he will be doing some operations, um, well, basically a lot of operations he will be doing, and then he will be adding this negative value, so he will be subtracting 0x30 from the resistor 10, and then adding that that value again back to the resistor 10. So the result of all this is going to be in the resistor 10. Okay, we tried to compile that manually later on in C, so that we can write the code in a high level language, so we can see much more better than this. Um, Next, what do we have? So after generating that resistor 10, or just calculating, let's say, a new pin, we are going to be calling the get from table. So the get from table is going to be taking two arguments. The first thing is what's in the resistor 14 and the resistor 15. So the resistor 14 is going to be the offset name. So since the latest thing that we did with the resistor 14 was basically passing down the offset of the name inside of it, so resistor 14 is going to be holding that offset for us. Um, and then if we go back a little, and then we will be passing the first entry inside the hash table that we have created also to the get from table. So the get from table is supposed to be returning something for us just by giving the offset name that we have gave, and we also give the address of the first entry that of the hash table that we have created. Yes. So we then after that we have to check if the result is -1. So if the result is -1, that means that so if the result is different to -1, that means that there is a result. So we jump to this address, which is this one, which is going to be XORing the generated pin with the result that we have, and then do an AND with that value, and then check actually this condition, and then it's going to be jumping to this one. If there is if the result of this operation is different to 0, then access denied. Otherwise, access will be granted if the result is greater or equal to the generated pin. Otherwise, access granted but account not activated if it is inferior to resistor 10. And yes, so the result should be greater or equal to the resistor 10 in order to be able to have the access granted. But this one is not going to be happening simply because as long as we have an equal. So basically, the condition that we have dealt with is actually the m is different. So if the resistor 15 is different to -1, then he's going to be directly giving you access denied, because that user um, is basically there but do not have access. But for example, if the result is equal to -1, then he will be calling no such a box, which is the message that we have seen when we try to run the program, which means that the user is not there. So we need a way to add a user inside of this hash table. So the way to do that is basically using this command, which is basically, we can just call it new, we can just call it whatever we want, as long as we basically want three characters, and we will see why we need three characters. So if the first character is not an A, is we need a character that starts with an N to be able to add a new user. So the first character is starting with an N, then that means that we will be basically going to add a new user. So to add a new user, we basically start the command with N, and we give the name and the pin. So we move what's in the resistor 11 into resistor 9. So resistor 9, we add a 4, which means that we are 1, 2, 3, 4 to get to the name. So this is the offset of the name. And then we jump back to this one, and we compare basically the result of the. Wait a second, did I just okay, so it's going to be this one, yeah. So we'll be comparing what's in the register 15 with -1, which means the result of that one, the result of get from table, just to check if the register 15 is having -1. But before that, wait a second, did I make that jump right? Because I feel like something is wrong. It's not the right. It's not the right, because it is 16. Okay, just a second. And that's not right. That's actually this address, which is this one. Yeah, this is the address. So he's basically going to be moving on the register 9 inside of the register 11. Then he will be basically getting the character pointed to by register 15 and doing the same thing as we have did with the offset name when we are going to be accessing some user. So this is the same thing as the one that we have did with the previous one. And then we will be comparing the result with the space. If it is a space, then we replace it with a null byte to mark it as a string, or to mark it as the ending of that string, and so on. And for the pin, it's going to be the same algorithm that we have did with the previous command. So we are going basically to do the same thing as the previous one. What else? So, and after doing all of that, we are going to be calling get from table, which is going to be passing on the offset name and the address of the first entry in the hash table. And the thing is that we want to make sure that we won't be adding the same user twice. So to do that, we will be using get from table. So if that user, so if the result is equal to -1, that means that there is no result. Then um, we will be jumping to this address. Otherwise, if there is a result, that means that the user has already an account manager, or an account basically. So we'll be printing back the message user has already an account message. And the thing is that we will be calling the puts. And the other interesting thing is that whenever you are seeing those messages that we have seen, he always move the message inside of the register 15 and then jump back to the call, and jump back to the function directly, which is basically calling puts. Um, okay, since the function is directly under the message, then we don't need to jump to the function because it's already the next instruction. So he will be printing the message user has already an account. So otherwise, um, if the user is not there, since the user, if the user, we didn't add that user, what are we going to be doing? So we will be pushing the register 10, which is the pin that we have generated, and we will be pushing register 9, which is the offset name, and we will be pushing the pointer to a string or to a message, which is adding user account. And then we call the printf just to see it in front of us, and then we clean the stack frame. We clean basically those 6 bytes that we have pushed, and then we set register 13 equal to the pin that we have generated, and the offset name, and the address of the first entry in the hash table that we have created, and we call the function add to table to be adding the that username or that user specifically to the hash table that we have. After doing that, we basically do clear the stack, and we have in here the invalid command message, and we basically return. So otherwise, so after just doing all of that, so the latest function is going to be doing this, which is this one, which is going to be going back to the stack, initializing back again everything and all of that. Okay. Now, after reverse engineering all that code, we can basically get an idea about the code just by trying to decompile that in C. By writing that in C, we can directly decompile that. So we're going to be including standard input dot h, and then I'm gonna be creating a main function that is going to be it is going to be the main that we will be having. So the first thing that we have to do is that for now we don't know any kind of idea about exactly what the table is having and how stuff is going to be structured. But let's just try, for example, to add, for example, a username. So for example, if you want to add a username, I'm going to be using new, for example, item byte, and the pin is going to be 01. So if we try to do that, we see that adding user account item byte with pin 01 is cool. It's working. For example, if I want to access that one, so I'm gonna be accessing the account, my account basically with the pin 01. Access granted, but cannot be activated simply because we do not have that piece of hardware that we need to be activating users. Okay. Now, if I want to reverse engineer back this code, I'm gonna be taking a note into everything that we have reverse engineered statically and take that back to the C language. So how do we do this? So this is basically a function. So this is the main. So it's going to be basically calling the run. So I'm gonna be calling that directly run. So since the main is going to be calling the run. So the function of the run is basically, so it's not a function, so it's a void, since it will be just reading stuff from the table and writing stuff to the table, so to the hash table specifically. So it's going to be a void. Yes. So the first thing that we have to do is we will be saving the old registers. So before the old registers, we have the stack. So we have to initialize the stack memory. So stack memo. So stack memory is going to be 0x600, and we have also a pointer to the username that we have, which is a string. We also have a pin. Okay, we also have a pin that we will be using. What else do we need to have? We don't have other things to do. Okay, now the first thing that we will be doing after allocating stuff is calling the create hash table. So I'm gonna be assuming that there is a structure that is called table. Um, and basically we need basically an array that is going to be pointing to this table. So I'm gonna be calling, for example, this table pointer, table pt, that is going to be called, or the result of the create table or create hash table is basically going to be return back to this pointer, which is table pt, because create hash table is basically returning a pointer. That's why I have created a function that is or actually that's why I have created a variable that is pointing to a table, to this structure that we will have to investigate later on. Just by investigating memory we can extract exactly how this structure is working, just as with the same as, for example, the challenge of jars that we have solved. Okay, so we are basically going to be passing on 3 and 5, and then we can just continue. So and then we have a lot of messages, so welcome messages. Okay, and then what do we have? So after doing the welcome messages, now we start doing, as long as we have, so we start initializing with 0. So this is where the program starts keeps on working. So while true, as long as we have the program working on, or for example, we can just set x equal to 1, as long as x, or as long as 1, while 1, yeah, we can do just while 1 directly. So while 1, for example, we will be initializing the stack with zeros. So we can just do that, for example, with a simple loop for int I equals to 0, e inferior to the 0x 600, e plus plus, stack memo of I equals to 0. And then we have to get something to this, we have to get an input. So basically the input is going to be read directly to the stack. So we can, for example, just call a get string function without defining that function. We basically know that it's going to be, we can just call it get string memory copy, you can call it whatever you want. So it's going to be copying that to the stack memo, and it's going to be basically reading 0x600 bytes of data, or basically 0x um, 5ff bytes of data. Okay, so after doing that, now we start doing what is actually just parsing the offset, parsing the name and parsing the pin out of that payload. So as long as we have, so we can just predefine a simple way of doing this, just by doing, for example, as long as, so the I is equal to 0, and as long as the stack memo of I is, so as long as there is a character inside of the stack that we can deal with. So if the stack memo, now we start with the conditions that we have. The first condition is the first character is starting with an A. So if the stack memo of I is, for example, equal to A, so if it is equal to A, then we start by extracting the username and um, the so username is going to be stack memo. We have to extract the username and the pin. So it's going to be stack memo of I plus 7 for the access command, since the name is at the offset of the access string plus 7. Okay, so and then we can just increment the I with a 7, and then we have to check the username, or we have to parse the usernames now. So how do we do this? So while the stack memo of I is basically different, or is basically just not 0, as long as it's not 0, um, we can just check directly. Um, so we can just do that as long as it's different to space. So if it's not a space, now we are trying basically to get exactly the username. Okay, or to get basically the space change. So we are going to be marking that space as a null byte. So if it is different to that space, then e plus plus, and then if we hit this space, so we are going basically to be hitting the space for sure. So then stack memory of I should be equal to 0. Yes. And then after doing that, we have to increment the I. So we are going to be now, so this is basically um, changing the with null byte. Okay. Now we are going to be generating a pin. So to generate a pin, we did actually those instructions, which are a lot of operations that we have to check on. Okay, so the first thing that we did is basically we have to create a short pin. So this is basically, yeah, we already defined them. We don't have to define them again. So pin is going to be equal to 0. And then as long as the stack is different to, as long as the stack memory is different to 0, then pin should be equal, pin should be equal. Okay, let's see, we have multiplied the resistor, so resistor 13 is equal to the resistor 10, and then we multiplied by 2, we added e, so this is basically multiplied by 2, so this is basically um, multiplied by 4. So 2, 2, this is a 4, we add a 1, this is a 5, we multiply it by 2, so this is a 5 by 2, which is a 10. So the pin should be multiplied by a 10, and then the pin we actually extracted from it 0x30, and then we added the resistor 13. So resistor 10 is actually, so we extracted 0x30 out of it. So before doing that, we actually added register 13 and we extracted that one. So it is basically going, register 10 is going to be plus equal to the stack memory at that position minus that one. Okay, so we are basically generating that one based on the stack memory at that position minus that one, and then we increment the counter. Okay. What else do we have? Yes. Okay, yes. But wait a second. Like all of that should be, wait a second. All of that should be if the stack of memory is different to the semicolon. So, yeah. We stop when the semicolon is there. Okay. Okay, so this is basically how we have generated all of that. So now we have now, after doing all of that, we have now to call the get from table to check if the username is there or not. Now, so I'm gonna be creating another variable. So um, pin pin table. So pin table is going to be returning something for us, or let's just call it result, for example. The result is going to be get from table. Get from table. We are going to be passing on table pt, and I'm gonna be passing on also these two instructions. Okay, which is the username and without a pin. Basically the pin is not gonna be passed. Okay, so this is the get from table. What else do we have now after doing the guess? So there was the result. So if the result is equal to -1, then uh, we obviously print f user. We can just put directly, so we are not printfing anything, so we are basically calling puts. So puts no such a box, no such a box. Otherwise, what else do we have? So otherwise we are going to be doing some XOR, some stuff like that. So let's just say we are going to be doing some operations, and then just other messages such as access denied and access granted, and yes, stuff like that. Okay. So yes, so after doing all of that, so this is just the messages. So yeah, now otherwise, so if it is not, the first character is not an A, so else if the stack memory is of I is equal to the n, it's not equal to the A, what would be happening? So the first thing we have to do is we have to get the username again, which is in the register 9. So username is going to be stack memo plus I, but this time it's going to be plus 4 since we are adding a 4 to that username. And then we will be needing to increment the 4, so it needs to be incremented with a 4, and as long as the we are going to be basically doing the same thing as this one. So I'm gonna be taking that one into this place since it is the same code, and for the pin it will be also the same thing. And after that, now we are not giving, so we need to check if the we need to check also, we need to make this check. So we need to check if the um, we need to check the result, so if the username so is there or not. So if the result is different to -1, so that means that we need to print user exists. So that means that the user exists. Otherwise we will be adding that user. So if the user exists, so otherwise um, we need to add that user exactly to the table. So how do we do that? Gotta be so get from table, so this one, yeah. So we need to add that user. So how do we add that user? So the first thing to do, we are going to be calling printf. So there's this printf that is going to be calling adding user, what is the function, add your using account, adding user accounts, and then let's say percentage yes, with pin percentage d. So and then we have the username and the pin, and we have the pin, yeah. And then we'll be adding to the table the username with that. We'll be adding to the table, to the hash table, that username with that pin too. Yeah, since we will be passing down 3 parameters, which are the pin, the username, and the table pointer, which is a pointer to the hash table that we have done. Otherwise, so if this command is not working, so we will be putting invalid command, and we will be basically above that we'll be printing the invalid command and also returning. Otherwise, if it's not working, so we have, so yeah, so this is basically what is going to be happening inside of this code. So we have successfully reverse engineered the code, that is the logic of the code, actually not the code itself, because we hadn't yet reverse engineered the hash tables. That is mainly the core, of that, of the challenge. Yes. So now after reverse engineering this code, what's next is, now I'm gonna be trying to dynamically understand how this hash table is going to be working. So to do that, I'm gonna be taking a look at the code that we have, and I'm gonna be trying to check. The first thing to do is check the create hash table function. So it's called in here, and the result is at the at the register, so at the register 8. So I'm gonna be trying to set a breakpoint there and see what is going to be happening. So I'm gonna be resetting, and then we have this create hash table. So I'm gonna be stepping a step. So register 8 now is having 1506. So I'm gonna be checking this address at the memory to try to know exactly what the hash table is. So it is 1506, which is this one. So this is the hash table. So as you can see, we have chunks of data, and if you have watched the video of Algiers or try to solve the challenge of Algiers, you should just see a pattern that is repeating itself, which is a kind of linked list where each block of code that or block of memory that you are seeing is basically a node. Where this is the previous, this is the next, and this is the size of the node on the linked list. So it is actually the same pattern, and all those nodes are actually allocated inside of the heap. They are not in the stack. So in the previous challenge that we have solved the gyres, so the heap was above the stack, and this time the heap is actually under the stack, which is a kind of weird actually. Yes. So we have to understand what are those values, and the next thing that we have to, so if we understood exactly what are those values, we understood exactly the hash table structure. So after some trials, and I did actually a lot of errors, I tried to understand exactly what are those, and it comes out that, for example, let me just take a snapshot on that and try to work on that. For example, just a second. I'm gonna be taking a snapshot on that. I'm gonna be taking that into the paint so that we can check that out. So I'm gonna be taking that one in here. I'm gonna be zooming a little so you can see the memory. So this is basically what the hash table is going to be containing. So it seems out to be that the first thing that I thought was basically just by looking. So this is going to be a place where we will be setting up the data, and those are actually the metadata of the node. So I'm assuming that you have watched the video of Algiers. So basically by looking at the code, so this is basically a red one. So this is basically a red one. So it is of it is it's not with the metadata, but more with the data block, since the nodes that we will be dealing with, guys, are going to be like that. So this is the first node, so it is going to be divided into metadata that we have dealt with. Sorry for the bad writing. And this is going to be the data, and the metadata is going to be pointing to the next block, which is going to be data and metadata, and so on and so on and so on and so on. So it's basically just a representation of how stuff is going to be on the heap. So the same thing goes for this one. So this is the metadata. So this is metadata. So this is actually the previous chunk that this node is pointing to. This is the next chunk that the node will be pointing to, and this is the size of the chunk. So for example, for in this case we have 3C15. So if we reverse the bytes that we have, since they are a little Indian, so it is 15 3C. If we go back, 15 3C is pointing to this block of data. So this metadata is pointing to this metadata. So if we can just call this, for example, entry 0, for example, in the hash table. So this is entry 0, this is entry 1, and so on. So I have tried to count all of them. So if we try to count all of them, so we have a 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we are basically, wait a second, we have 0, 1, 2, 3, 4, 5, 6, and we have a 7, and we have an 8. So we are basically having 8 entries. Yes. So if we try now to check what are those exactly. So now the interesting thing is that this is actually an entry point, and this is actually another entry point, and this is actually um, where some stuff is also allocated. So it's a kind of weird because simply, as you can see, for example, when I had those zeros, I've assumed that this is actually a node, and yes, it comes out that this is actually a node. So this is a node, and as we can see, it's actually pointing to that node. So the previous of this chunk is going to be pointing to this one, which is 1526, which is this one, and the next is going to be 159C, which is this one. So this is 159C, which is pointing to this one, and etc. So I don't know exactly, to be honest with you guys, what are those instructions, where, what are the meaning of those values inside of those entries, but I tried as much as I can to just reverse engineer what the hash table is going to be having. And comes out that, for example, this value is going to be pointing to the entry, to an entry. For example, 1542. 1542 is actually this one, which is this one, just starting from this one. And for example, 1582 is going to be pointing to this block of data. So those values that are in here, for example, this one, this one, this one, this one, this one, and this one, this one, and this one, are going to be actually the entry points, or the a pointer that points to actually the data blocks of the entry that we have. And when we try to count them together, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 entry points of data, and each entry point of data is going to be having its own metadata block, which are the 6 bytes that we had, which are the same as the gyros values. But for this challenge, we have a bigger size of a block. So that means that for each block of data inside of this linked list, it's going to be having a lot of data. So yes, but the interesting thing in here is that this block of data is not allocated. So that means that the blue one is not listed as a place where we can save data. So that means that the saving of the data starting from this one, which is the entry 0 that I've assumed that is going to be entry 0, and this is going to be the entry 1, and so on. So yes, so this is how stuff is happening. And the thing is that the latest entry point of data that we can add, or that we can save data to, is going to be 52E2. So 52E2. So it is going to be this one. So this is this is E2. So this block of data is not with them. So that's why we have 0, 1, 2, 3, 4, 5, 6, 7, and we have an 8, which is this one. Well, the 8 is not counted because simply there are 8 entries. So we have basically 7 minus 0 plus 1, which are 8 entries. Yes. So this is basically how stuff is going to be happening. And another interesting thing, so since those are entry points to the data blocks. Again, we have those three values back, which are actually the metadata of this block of data. And we have also this metadata block of data. So this is the metadata, this is the data, this is the metadata, this is the data, but this time the data is actually pointers to all the entries, and we have also this metadata, and we have this data, which I don't know exactly what is the purpose of this, for example, block of data. And then we have the blocks that is going to be saving data. And the thing, or the idea, or the question that can be arised in here, for example, how did you know that this is going to be saving data and this is not going to be saving data? For example, the blue one is not going to be saving data, and the data can be saved, for example, into this one. Now, I already knew that actually by trying to just test the test the program and run that. For example, I kept on running the program, and I tried, for example, to add, for example, AA, for example, with a pin 1, And when I tried that, actually, it came out, as you can see, that this is the entry 0 that I have talked about, and it's having 61, 61, and the pin 0. And the interesting thing is that the offset between the username and the pin that I have gave is actually the username is taking 16 bytes of data, and the pin is has took actually one or 2 bytes of data. So that means that if I try, for example, to add one more user, it should be with that one. So for example, 02, if we try to add that one, we see that we have this is the username and this is the pin. So that means that we keep on, as long as we keep adding users to the hash table, they are going to be set to the entry 0. Now the question that arises here: how do I know that the username AA and the username BB are going to be added to the entry 0 that is located into this space? Now this is where I spent a long time basically trying to understand how this hash table is working. It's basically trying to reverse engineer the function of the hash. So if we try and check exactly where we have called the hash, is basically going to be in the add table. So if we go into add to table function, so it is basically in here. Yes, so the add to table function is going to be adding a username to the table. And how did I know that the AA and the BB is going to be basically added to the entry 0 is by trying to reverse engineer the hash function. So this is the new hash. I want to have the hash function. So this is the hash function that is in front of you. It's not that big, but it's basically taking the username in our case, and it's going to be hashing that username into something. So to understand more, what is this happening, how this is happening, and why this is important, I have tried to research a little into the internet just to understand how hashing functions work. So basically, hash functions is a hashing mechanism that is going to be used. So it's going to be taking a key, and then it will be returning basically an index, and then it will be putting the value. In our case, it's the pin, um, mapping that value with the index that is going to be generated by the hash function. So in our case, we are basically having 8 entries. And if you remember, if we go back a little, if we go just back a little, we see that we have passed to the create function, to the create hash table, two values, which are 5 and 3. And if we go back a little, we see that we have, for example, in here 5, we have a 3, and we have a 5. So this is basically the metadata of the table, and those are the two values, and we have other two values which are 1560. So 1560 is basically um, this the different addresses of the entry points of data that we have. And we have 152C. So 152C is actually pointing to 152C. Okay, 152C is pointing to this value, which are this one, which is this block of data that I don't know exactly what it's going to be doing. And 1500, which is actually the metadata of this one. And yeah, so this is basically just for the table, and we have this one for the next as the net for the next block, which are this is the metadata, and those are the values of that metadata. So those are the data of that metadata that we have in here, which is this one. Anyway, the question that rises here is that when we gave it 3, it's actually somehow some kind of power of 2. So it's actually 2 to the power of 3, which means that we are going to be creating 8 entries, with each one of them having actually a fixed size, which is going to be actually, in this case, 5. Anyway, just by trying to understand that, I just figured out somehow some of what is happening inside of that table. Now, the question that arises in here is that when I came back to the hash function that I needed to reverse engineer is that I want to know exactly, I want to predict, this is the thing, I want to predict, for example, where the, for example, username AA with a pin 0 is going to be inside of those entries that I'm having. For example, when I say I'm gonna be adding DC with a 02, I don't know where this DC is going to be added. It's not in the entry 0 since there is nothing in here, but it is in this place, which is in the entry 1, the one that is under the entry 0. Now, we needed to this is why we need to reverse engineer the hash function. So from what I've understood, the key in this case is going to be basically the username, and the value is going to be the pin. And the hash table is going to be mapping basically the username with the pin. And that's why to get, for example, something from the table, you only have to give the username. You don't have to give the pin, because he is going to basically check in the hash table the username pointed to, but that the username pointed to the pin basically pointed to by that username, and if there is a result, then there is a username and there is a user basically, otherwise there is no user inside of the hash table. So this is why I had to reverse engineer this little code, and we have to reverse engineer that code together. So if we go back a little, so to the hash function, so the hash function is going to be taking the username, so register 14 is going to be having the username, and register 15 is going to be 0, and then we move what is the username, what is the character pointed to by register, what is the character pointed to by register 14, which is containing um, the offset of the username, and then we are going to be doing a lot of operations. So the first operation is sign extend. We can just ignore that for the moment, and register 13 is going to be register for 15, which is actually the ASCII of uh, is going to be the ASCII of the ith character. Register 14 is like that. Okay, and then we are going to be incrementing the register 14. Okay, so this is register 14 plus plus. Okay, so what do we have next? So we are going to be doing a lot of operations. So register 15 equals to register 15 plus um, plus, so it's just the register 13, and register 15 is going to be register 15 plus register 15, which means that it's going to be so just multiplying by 2, multiplying by 2, multiplying by actually another 2. So this is actually multiplying by 2, and then multiplying by 4, and then multiplying by 8, and then multiplying by 16, and then multiplying by 7, well, 32. So this is 2, 4, 8, 16, 32, and then we subtract from it 13, which is actually multiplying it by 31, since we subtracted just a 1 from the register 15. And then we test if it is a 0. If we hit the end of the username, and then yes, we return. So basically the return is in the register 15. So if we try to reverse engineer this function, we get something like that. We can just write that in Python, for example. So it's going to be defining hash. It's going to be taking the username, and actually the username is, so the hash function is going to be returning the index. So the index, for example, in our case by default um, is going to be actually the entry 0, which is this one. Now, how do we recalculate that? So for a character in the username, I'm gonna be actually taking the index, which is going to be the first thing, the ASCII character of the ASCII of the character, and then I'm gonna be multiplying that index um, by 31. Yes, I'm gonna be multiplying that by 31. And then I'm gonna be returning that index. So this is what the hash function is going to be doing. But the thing is, if we take a look, for example, at this hash function, it needs to be all the results should be in the range of the size of the hash table. In our case, the hash table is having a size of basically 8 entries. So we should be trying to get all the so we can just simply number of entries. So to get the result of the hash function and the boundaries or in the range of the number of entries, so we have basically 0x8 entries, and we want basically to return the index modulus. So to get them in the range of the number of entries, we can just add the modulus number of entries. And for example, if we send now, for example, I'm gonna be hashing. I want to hash AA, for example. To hash AA, it's gonna be 7. Well, is there anything that we have did wrong? Well, yeah, because simply we are going to be adding the ASCII code and then multiplying by 31, because we already see that in here, which is this instruction, which is adding what's in the register 15 to the register 13. We are not moving directly that value. If we try to set that back, we see that sending NA is going to be a 0, and if we send it DC, it's a 1. So this is why simply when we have set, for example, when we have sent a DC, it's going to be in the entry 1, which is this one. And if when we send the AA and the BB, and what about the BB? Let's see. BB, what's it's going to be having? So it's a 0. So this is why the BAA and BB is going to be sent to the entry 0, and DC is going to be sent to the entry 1. So this is how I reverse engineered basically the hashing function. Now, after doing all of that, there is only one thing that I needed to add to my code to reverse engineer completely what is happening, is by creating the structure of the table. So to create the structure of the table, I needed to just take a look at this table and understand each one of them. So I don't give too much attention. I'm not going to be giving too much attention about the metadata of the table. But what's really interesting is that the table is going to be pointing to exactly the entry 0, entry 1, etc., 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 and it's going to be having other features. So, for example, the first feature is going to be the total size, and the second feature is the amount of entries that we have, which is this one. For example, this one, the total size was somehow 0 in this case. I don't know why. So we can just call it total size or something that I know, random attribute that I don't know exactly. The next thing was actually this one, which is the number of entries. Uh, and the next one is the number of cells in each entry. Number of cells. And the next one was actually pointing to the entries themselves, which is actually a pointer to this one. So this is not, this is a value, this is a value. Now this is a pointer, so this is an address. So it's going to be basically pointing to an address to a user. So this is, for example, entry 0 is for a user. It has its own metadata, and the block data is actually for a user, where each user is going to be having 16 bytes of data and a pin. So we can define, for example, another structure for a user. We can call it, for example, user is going to be having for example, a char username that is going to be 0x10, which is 16 bytes of data. It's going to be having a pin, and yes, so this is what a user is going to be having. And then we are going to be pointing to a user So entries, each entry is going to be pointing to a user. And the last thing that I have seen, which is this random value that I don't know exactly what this thing. So we can just put it basically something that is going to be pointing to a short random attribute, another random attribute that I don't know exactly what it's going to be doing. For now, I didn't dig too much about what is the meaning of this 15.2c, which is actually this thing, this block, this blue block of data, or this block or node, or you can call it whatever you want. I don't know exactly what this thing is going to be doing. What I know for now is that when you create a table, it's going to be creating those entries where our input is going to be done. We have reverse engineered the hash function that is going to be mapping the username to its pin. When we add any kind of username inside of this hash table, now there's only one thing that is we have to do. So I fully reverse engineered now this code and what is happening inside of it. I only have one thing that needs to be done now. Just after taking a look at this code, I needed to understand how I can exploit such a thing. Now we pass down to the part where we have to exploit so this thing. So the thing that I tried to do was basically, guys, just as I did with the Elgire's challenge, is basically by trying to. So here's the idea. So the first thing we do is basically we try to check, for example, the return address. So by checking the return address, so I wanted to go to the main. So we go to the main. The main is actually calling the function run. So if we try to override the return of the main, for example, into another code that we will be loading, for example, in one of the entries and then returning back to it. So basically by trying to chain some, let's say, some gadgets and try to do some return oriented programming exploit, we can basically do something with this challenge. So this is my idea. So my idea is basically, so this idea basically came at the fourth day. Just after reverse engineering everything, I took some time to exploit that because a lot of errors have been happening to me, and ah, it's just a nightmare just trying to exploit that. Okay, so just to simplify things for you, we have a run function that is we are calling basically the run function, but we are returning to the main. So if I try to set a breakpoint in here, so if we try to set a breakpoint in here, so just to understand or know exactly what the return function is. So if we set, so this is the return, the call to the return. So if I step a little, so now we are in the return. Now if I go and check the stack pointer, the stack pointer now is having this address, which is 44.3e. If we go back a little, so this is the next instruction that we should came back when we finish executing the run function. Now the idea is the same idea as we did with the Elgire's challenge. It's going to be a heap overflow exploit. I'm gonna be trying to overflow the heap to go back to this place exactly. I'm gonna be assuming this is going to be a fake chunk. This is the size, this is the next, and this is the previous. I'm gonna be trying to return to this place is specifically by trying to return to the address 43f2, just by assuming that this is actually part of the heap, and then try to change the size. And after I change the size of this fake chunk, I'm gonna be just trying to make the run function return to the new return address that is also the same as the size in this fake chunk. So this is the idea. So it's basically the same as the Agiris video. If you hadn't watched the video of the Agiris, this came back to exactly understand how this exploit is working. And basically the work um, to exploit such a vulnerability, we basically need to understand how the free function is working and how the malloc function is working. But this exploit is specifically on the free, so I had to check where the free function is called, and somehow the free function is basically called with the rehash function. Now comes the part where I had a lot of code to check, which is the rehash function. So the best way to do that, to gain some time on that, I just check this. So I just try to check how exactly the rehashing is working in hash tables. So rehashing in hash tables is the process of increasing the size of the table and reassigning all elements to new positions. So this is why we are actually using the free, because we are actually reassigning all the elements. We are repositioning or reallocating the chunks that we have inside of the heap into other places. So hash tables are a type of data structure that uses a hash function to map keys to a specific position in an array. However, as more elements are added to the hash table, the likelihood of collisions where two keys are assigned to the same position increases. So this can lead to a decrease in the performance of the hash table. To mitigate this, we use a process called rehashing. So rehashing involves increasing the size of the hash table and reassigning all the elements to new positions. So this is typically done when the load factor or the ratio of the number of elements and the size of the table exceeds a certain threshold. Now the question that comes into my mind: what is the threshold inside of this microcorruption challenge? So this is where I tried to keep sending users to the hash table, trying to see when he is going to be calling the rehash function. And I tried to do that by setting a breakpoint at the rehash function, and I kept on overflowing the system with users until the rehash function was called, and I just noted the value, and it's actually 10. It's actually 11. Yes. So I had to insert 11 users and then adding 12 to get exactly the rehash function called. So as a conclusion, this rehashing is going to be increasing the size of the table by reassigning all the elements to a new position. So if we try to go back a little, rehashing is going to be basically taking this, for example, if there is a value in the side of the entry 1, it is going to be assigned into another place, and we are going to be actually resizing the table and getting the values of the getting actually the users that we have into other places. So that's why we are calling the free, to free the old place and to get them into other new places. So since the rehashing is going to be calling the free, my idea is like this: I'm gonna be loading my code inside of the entry 1, and I'm gonna be trying to change the previous of the previous of this block of data, which means that I'm gonna be trying to change the previous of this one with the address of the return address that we want, which is 43F2. That is actually going to be pointing to this one. I'm gonna be changing the previous of this block of this entry one to the previous as the fake chunk that we want to change. The next is a question that I've been asking a lot when I had to solve this challenge, because I had a lot of errors and the exploit won't work because of this next that I'm gonna be talking about. And we need also to calculate the amount of size needed in order to be changing this 443E into the desired address code that is going to be 15A2. Yes. Okay. Oh, so this is an idea, or we can actually. So, guys, the thing is that we can actually either set the code in this place, or we can set the code in this place. So it's up to you to do that. We can also set the code into this place, so whatever. But for now, I'm gonna be setting the code that we will be executing. That So the code that I'm talking about is actually, guys, the code that will be opening up the door for us is actually the code that we will be returning to after we override this return address exactly. So let's assume I'm gonna be writing a code that is going to be unlocking the door, and I'm gonna be loading that code inside of the entry 0. And then I'm gonna be trying to override the previous of this one. We can override that one. For example, to override that, I tried basically, if we reload the challenge. So to overwrite, I'm gonna be trying to say, for example, I'm gonna be setting AA0, and I'm gonna be sending all of that 1, 2, 3, 4. For example, if we try to do that, I'm gonna be adding another one, which is a 5. So if we try to do that, we see that if we wait a little, so if we go back a little, so what is the entry? 0. So yes. Wait a second. Oh yeah, just a second. Uh, User has already an account, so that means, oh, okay, just a second. I'm gonna be changing something. 1, 2. So if we reload this one, the thing is that I kept on sending the same user. So okay, I'm gonna be resetting that again. Okay, we have to reload the challenge again. I want to just show you how we can override the metadata of the next block. So this is basically the vulnerability that we have. So 2, 3, 4, 5. So I'm gonna be changing the values. For example, this one is BB. And the thing is that we need the hash of those nodes. The hash of each username, for example, is to be the result of basically 0. So to check that, I had to just go back to the hash function that we have, reverse engineer, and check, for example, with the EE it's 0, with the DD it is 0, with the um, CC it is 0, and so on. Yeah. So this is basically how I checked that out. So that means that when we will be sending all those, so A, B, C, D, we can just, for example, send E, for example, EE with it. All of them are going to be sent basically to the entry 0. So if we try to check that out, we see that user already has an account, A, B, C, C, D, D. Okay, whatever. If we go and check that out, we see that we have them like A, B, C, D, E. Okay. Now, if I try to add, for example, AA, for example, new FF, for example, and 0, it's going to be changing the metadata of the next block. So this is exactly what the vulnerability is in. So that means now, if we go back a little, since I can override the previous and the next of the previous and the next and the size of the next block, that means that if I try to change them, override them, and then try to trigger the free that is exactly going to be called in the rehash function. So that means that I need to trigger the rehash function by sending enough amount of users to be calling the rehash function that is going to be resizing the table. Then when it's going to be resizing the table, it's going to be checking the previous and the next and the size. And when it's going to be freeing, for example, this block of data, the same methodology as the Agile challenge, it's going to be taking down the size of the previous one, and then um, going to be linking that one with the size of the, so it's going to be taking the size of the previous one with the size of the actual one, and then freeing the previous one, which means that it's going to be changing the size of the previous block. And the previous block is going to be the stack pointer that we will be pointing to, which is actually the return address that we will be triggering later on. So now if we try to exploit such a thing, we can write the exploit now. So the first thing that I'm gonna be doing is I'm gonna be trying to craft something that can open up the door for us. Well, the interesting thing is that we cannot use, for example, the code that we have used, for example, to directly unlock the door, which is actually moving 0x0 to the program counter. So we have used that code a lot. The problem with that assembly, with that code, that is actually containing 0, 0, and as we have seen, as long as the username is going to be is going to be having zeros, it's good. The rest of the code will be skipped. So that's why we need to craft something. It's more like crafting some shell code that does not have any zeros. So to do that, we can simply by taking a look, we have the interrupt in the code. So we can build something just using this interrupt. So by doing, we can just move, we can push, for example, we can push 0x7f just as the simplest way, or just by simplifying things, we can just directly do, for example, move 0x7f inside of the resistor 15, then push the resistor 15, and then call the address of the interrupt, which is 4c, which is 4CEC. So by assembling that, we still have those zeros. So how do we get rid of those zeros? Well, to do that, we can simply, for example, XOR resistor 15 with resistor 15. By doing that XOR, we are actually just, it's the same as moving 0 to the resistor 15. Because when you XOR a value with itself, it's going to be actually cleared. So yeah, so and then we can, for example, move 1 byte of data from, for example, by sending, for example, like that or whatever. So for example, 22 7f to the resistor 15, and then we move only 1 byte out of it. So if we assemble that, we get this value, which is this one. Now if we try to disassemble that, we get XOR, but we missed those two twos that we have sent. So to get them back, we can just add them manually, and we have this code. Now this code is going to be moving 1 byte from 7f to the resistor 15, and we don't have any kind of zeros inside of that code. So it's completely clear out, so it does not have any null bytes, so that code should be executed perfectly. So how do we inject that code? Now the interesting thing is that when we pass down this to the hash function, so it's going, well, it's not reading that right, so I'm gonna need to check if C is equals to, if type of C, well, if the type of the username is equal to bytes, then you don't have, so index is going to be plus equal to C directly, else it's going to be, so if I pass a string, then it's going to be directly like that. Yeah. So if we try to send that, so if we print C, okay, just a second. So yeah, so this should be bytes from string. This problem, bytes has no attribute from, well, bytes from hex, not from string. Okay, so yeah, so it should be working well. So it's 7. Well, this is a problem. Okay, now we need to, since I'm gonna be sending this to the entry 0, I want this code to be exactly into this place. We need to make it, we need to make its hash actually equals to 0. So how do we do this? So the first thing is that I'm not going to be sending exactly that, I'm not going to be exactly sending that code. So we need to exactly now find a way to do this. So how do we do that? So the way we can do this is, but this is a problem actually. We have to make sure that this one is actually equal to 0. We have to make sure. How do we know this? What if we change, for example, what is the thing that we can change into this code? We can change, for example, is to into 1, for example, and see what is going to be happening. So we disassemble that. Well, yes. It comes out that the 2 ones can be actually equals to the 0. So by sending 2 ones instead of 2 twos instead, just by changing these two values, we actually, the hash is now into the entry 0. So if we send this, to the entry 0, then this is going to be cool. So unlocking door. So this is code to unlock door. So loading code to unlock door for us. It's going to be so it's going to be printing bytes of actually new plus bytes from hacks of this code plus actually, so the thing is that we have to add a space since we do this new and space and then this code, and then we have for example E0, and yes, we don't have other things to add. I think, do we have other things? Nope. So it's going to be just hexified. So we need to hexify that. So I'm gonna be trying to add this one. So if we try this, what do we have? Cannot concatenate string with hex. We need to just make this a byte, and yes, we have this one. So if we send this code, it should be loaded inside of the entry, inside of the entry 0. So if we try to just now reset the whole program, what do we have? So we continue. If we check the as it encoded, and we see that the user account with that pin is, if we check the memory, check to see if it is entering inside of the entry 0, and yes, it is in the entry 0. This is the code and it is in the entry 0. The best thing that we have did for so far in this challenge is that we have reverse engineered the function, understood that hash functions are basically taking an input and then calculating some hash and then getting that hash inside of the boundaries that we have. In our case, the number of entries that we have is 8, so that's cool. So yeah, so after doing that, now we have to try to just add some other users. Just try to add some other users, for example, to overflow those two values, which are the next of the entry one, the previous and the next, and the size um, of the next block that we have. So I'm gonna be just printing some. Let's say I'm gonna be sending new, for example, I don't know, for example, BB or AA, for example, 0. I'm gonna be taking that. I'm gonna be repeating, sending that 2, 3, 4. 4 times is enough since we know that by sending 5 elements we get to the metadata of the next block. So we already sent one, which is containing the code. Then I'm gonna be sending 4 to get to the next metadata that we have. So I'm gonna be sending that one. So BB, CC, and we have DD. Okay. So that's cool. That's cool. Yeah. We don't have this. We don't have to send them in bytes. Uh, okay, so this is good. So if we send that, now we don't have to check the hex encoded input. What is the problem? Is there any kind of problem? Let me reset that. Okay, if we continue, I'm gonna be sending this code, and then I'm gonna be sending this code. Okay, all the users are added. If we wait a little, I'm gonna be checking the memory for that. So all the users are added. Now we are just one far away from overriding these two values that we have, which is the previous and the next and the size. Okay, now we need to override those values. So to override those values, I'm gonna be just the previous is gonna be, for example, bytes from hex. So what is the address that we need, for example, for the previous? So the previous is going to be actually the address of the stack pointer that we have seen, which is going to be 43 something. Basically it's 43. Yeah, so this is the return address, so I'm gonna be setting the previous as this one, just by assuming that this is the previous, this is the next, and this is the size of a fake chunk that I have just invented. So it's 43f2, so 43f2, so it's basically, if we just flip them together, so it's f2 43, and for the next Uh, Next it's going to be bytes from hex. So for the next we need something that makes sense actually, and I'm gonna be explaining this one. And for the size, it's actually going to be, so to know the size. Okay, so for the size, so what do we have? So we actually want to change, so this is the next that we will be overriding next, and it does not matter for the next. The next of the fake shank is something that we don't have to worry about. What we want to worry about is the size of the fake shank, since this is the value that will be changed by the free function. So the free function is going to be adding some other size to this actual size. So what will be happening is that the free will be taking this address, which is this size, which is 44.3e, and we'll be adding a 6 to it, since the 6 is actually the size of the metadata um, of the previous one. Since 6 is the size of the block of the metadata and the previous one, and then we need to add some value that we will be searching for to get exactly to the address of this one, which is the address of the code, which is going to be starting from this one, which is 1543 basically. Yeah, it's going to be 1543, or is it going to be 1542? Yes, it's this is 012, so it's 1542. So if we go back a little, so it's 1542. So what is the value that we should be adding? So it's going to be 1542 minus that one minus 6. So if we use Python to calculate that value, we can just directly calculate it in here. So it's going to be printing this value minus these two values. So to get to the value exactly that we want. So yeah, so we want to search for the value. So what is the problem? From hex takes exactly one input, so let's say I'm gonna be, for example, f2. There's some values, I'm gonna be changing them. So if I want to hexify that value, so it's going to be C0A. Okay, then we have a little problem. Well, the thing is that value right? Because that value looks okay. We are going to be, well, it's not 44. Is it 44? It's 43. It's not 44. 43F. Wait a second. Well, is it 44 or 43? Now I'm getting I'm getting confused actually. Okay, just a second. It's actually, yeah, 44. Is it? Yeah, it's 44 3E. Yes, this is a value that should be in there. But the problem um, is how much data do we? Yes, 44, 42. We need to. No, it's not plus 6. Come on. Yeah, so this is the value. Yeah, so this is the value that we will be. I just get confused because something was somehow kind of weird. Because we had to, because when I try to solve the challenge, that was the value, and I was just confused because I didn't get the same value that I was calculating. So yes, so we basically know how much data we need to add. With plus 6 is actually by default we will be adding 6 for the metadata of the previous block that we have freed, and with the value actually of the size, which is I'm trying to be setting in here, we should be getting 1542, which is actually the address that will be pointing to the code that we will be executing. So we want basically this value to become into 1542. So I'm trying to calculate how much value of the size of chunk I need to be setting in order to get to this value. And we basically need to set BFE. But the thing is that we know that the size is holding also a special flag, which is actually the flag uh, which is actually the flag of the malloc, which means that this flag is going to be telling the free function that this block is allocating, and it's actually the first bit. So that's why we need to make the, for example, BFE into BFF to make sure that the first bit is actually a 1. So that means that it's allocated, so he takes that chunk of data into consideration. So I'm going to be setting that, for example, into FF um, 0p. So basically, since we have 0p so we need to flip them together, and then we need to figure out exactly what is the next chunk that this one will be pointing to. So the next one that this one will be pointing to. So what I have tried to do is I tried to play that around. So the first thing that it did was setting some random data, some random address, I'm sorry, and somehow it throws some error to me, and the payload does not work and the exploit stopped working. So that was a problem. So the first idea was to throw an address, and then I tried the next address, and then I tried to set the next address, which is going to be, for example, 51BC, etc. But it comes out the only one that worked for me is the latest address, which is the next address is going to be the latest entry, which is the 8th entry. And to calculate the latest entry, I had to calculate the offset between the first, between, for example, one of the entries, and then just calculate them together. So, for example, for this entry, we have 15, for example, 3c. So just to calculate the offset between one entry and another, so it is 0x 15 3c. So I'm gonna be subtracting, for example, 15 9c, 15 9c minus that one, and it comes out that it is 96. So it's not 9c. Wait a second. Yes, it's 9c, and we have 3c, 15 3c. So it's 15 3c, and the next is 15 9c. Yeah, so yes, it's that one. So to know exactly what is the latest one, I had to just do a simple math. It's actually, so plus 0x, so it's plus 96 multiplied by 8 to get exactly to the latest entry, and the latest entry is actually 53 3c, which is this one. 53 53 3c, which is this one. Yeah, so this is actually the latest entry. Yeah, so I had to basically just set this as the next instruction. So if we go and set this one, so 53, so we have to flip them again, so 3c 53. So we have now the previous is going to be F243, which is going to be pointing to the fake chunk that I have just set, which is the fake chunk is actually living inside of the stack that we want to change. 3C53 is going to be in the next chunk that we will be freeing, and the size is going to be FF0B in order to be getting exactly the return address that we want to return to. Now, if I'm gonna be printing those values together, so I'm gonna be hexifying them. So the first thing we have to send is new. Then I'm gonna be sending the previous plus the next x plus the size plus. Well, actually, by doing that and just adding, for example, b, and we have a space and 0, and for example it is over there. For example, by doing that, there's a little problem actually. For example, if we do that, um, what do we have? So if we try to, just a second, we don't need that. So we have this thing, but I want to hexify that for a second, so we get this value. Now if I try to use this value, so we want this value basically to go where exactly? So this is the interesting thing. We want this value to go where exactly? So we want it to go into this place, which is the int 0. But if we try to send this, for example, value and check the hash of that value, just a second, it's actually e4, and we want it actually to become to give us a 0 to make this payload or to make this code goes to the int 0 to be able to override the metadata of the next chunk with the values that we want. So how do we do that? Well, I had to add some other values to it. So we need to add some other values to it. What I tried to add, for example, the byte, for example, 0x41. Well, by adding that, for example, I didn't get the hash that I wanted to. But when I added, for example, I basically tried a lot of bytes until I get that, and I actually wrote a script for that. Okay, just a second. Well, it's not in here. Just a second. It's not in here. Oh, my bad. I'm getting a little tired just by explaining this challenge. You don't know any idea how much time I have invested into this challenge. Okay, we get it 0, so that means that when we will be sending this, it will be going on into the entry 0. Okay, so if we send that, so I'm gonna be checking the hex encoded input, then I'm gonna be sending that one. So yeah, we have changed the metadata of the next one, of the next blocks. And we have F243, 3C53, FF0B. Now everything is cool. Now what we need now to have is we need to find a way on how we can trigger the rehash function. And as I have explained and as we have seen, there is a threshold that is going to be checked in order to be able to make a rehash on those in this hash table. So how do we know the threshold? I have tried several. I kept on actually overloading the system with users, and it came out that I need to be sending exactly 12 users in order to be able to call um, the rehash function. So we already sent one user, and we have sent four users. So what we need to send now, we already sent now 5, so we can just simply try to send, for example, um, another 5 users, and then we send, for example, 6 users or something like that. So for example, we can just send print as much users as we can. For example, A0, new B0, new C0, new D0, new E0, for example. So we have A, B, C, D, E, which is 1, 2, 3, 4, and 5. So those are 5 users. So 5 plus 5 is actually 10. So we will be sending 10 users. I wanted to send, for example, the first time I tried that when I just figured out that the threshold was 11 is by sending directly sending this code and sending those 4 users just to overflow to get to the metadata of the next block. And then I tried to send 6 users at the time, but it seems out that 6 users is not accepted. The maximum users that you can send is actually 5, just using chained command like that. So we had to send that one. So we can send directly this. So by sending that one, now we have to uncheck the hex encoded, and by doing that, we have added the users. They should be in one of the places that are in here. We have a problem. CPU is off. New C, new D, new E, whatever. Like, let me just reset that again and try to send them back again. If we check that, I think this is because I didn't check something. Maybe, I don't know. Okay, so the users are added. We have to check that. That means I'm gonna be checking that. The user is added. There's a problem. What is the problem exactly? Hmm. where is the problem? Okay, let me just check that out. What is the problem? What is the problem inside of that? New D, we have a 0. Mm, let me just check that out. Mm. Oh, I think the problem is because of the new. Might be those spaces I have added. There was no spaces into side of that. Try to add use this one. Okay, we have to reset again once the CPU is off. Okay, I'm gonna be sending the code, and I'm gonna be overflowing until we get to the metadata of the next one. Then um, I'm gonna be changing the metadata, and then I'm gonna be trying to call the rehash function, trying to trigger it. So pins are working now, and then to trigger that we only need one value now to add, which is new, for example, f. There's an example now, for example, f0. And now if we try to check, for example, the hash function should be triggered if we check that. But the thing is that if we try to check, for example, the stack pointer 43F2, and this is the interesting point, that now the address is pointing to 53 3C, and the address that we have as the size, which is actually the return address, is 1542, which is actually pointing to this one, which is 1542 is actually our code. 1542, what is exactly 1542, 1542, which is the code we have, which is this one. So if we now try, for example, to continue, how do we execute that code? We have to send an invalid command, for example, quit, and boom, the door is opened. This is actually, guys, one of the best challenges that I have played by so far. You don't have any idea how this challenge just gives you just an idea about how hash tables working, how exactly heap overflows are so powerful. Like, to be honest, if I hadn't the chance um, to just basically override the values of the next metadata block, I won't be able to exploit such a thing. And the glory of that is that I didn't check even any kind of solutions. I tried basically to solve that on my own. This is the interesting part, that I spent too much time involving myself into this just to basically get the unlock door satisfaction. So yes, so we will be just doing now a little recap since this is the end of this series. We have seen format string vulnerabilities, we have explored buffer overflows vulnerabilities, we have explored heap overflows vulnerabilities, we have explored basically, we did a lot of something called return oriented programming chains. So one of the few things that we have is by you load the code and then you return back to your code. It's basically return oriented programming. What else did we do? We did a lot of reverse engineering. We basically learned about just a little idea about emulators, but we didn't get in depth about that. I might be just making videos about emulators, explaining in depth what emulators are doing, and I'm making my own researches, guys. This is the interesting point, that I'm making my own researches. And yes, hats off to the authors of the microcorruption challenges. It took me actually 4 months to solve all of them, but I had a lot of fun. I had a lot of fun solving that. So yes, so if you have enjoyed this series of videos about microcorruption challenges, write me in the comments what are the next challenges that we want to solve with me together. And if you have any idea, if you have any question, if you have anything, just hit me on Twitter. Just send a message. Don't worry, I'm gonna be responding. I'm not the kind of persons, not like people who say, "No, I don't have time." Like, I have time to answer questions. Just ask me. Yes, so if we solve that in the server, to be honest, let's just solve that on the server just to get the satisfaction um, of just solving that on the server. So we add just that one. We quit. The lock did not accept your input. Try again. Like whatever, just whatever. We have solved that. Anyway, yes. So if you have any kind of if you have any kind of questions, just ask me, guys. And yes, so see you on the next video. Bye.